I am trying to tape the lectures. I have been trying to tape the lectures. I'm not sure I got the first one, chapter 10. I'm not sure I have it. And before we leave today, I'm going to show you on Canvas homepage where you can access these. So today, tomorrow, if you so desire, you can go back, and you don't have to listen to the whole lecture. You could go in there and say, well, I just want to find that part about this or that or the other thing. So you can zoom ahead or back or get in there and listen to 10 minutes of a particular part of it. All right, so yesterday we started chapter 12. We talked about what alcohols are, some of their properties. We talked about primary, secondary, and tertiary alcohols. Got into how to name alcohols. So let's name this alcohol right there. Name that alcohol. What's the parent name? It's 5 carbons long, and this is going to be carbon number 1. 2, 3, 4, that's going to be carbon number 5. So what pentanol is it? 2 pentanol, 2 methyl. Two methyl, 2 pentanol. Okay, how about this one here? And I've numbered the carbons. So its parent name is, let's see, I better plan ahead here. Hexanol. Which hexanol is it? 1 hexanol, 5 methyl. 5 methyl, 1 hexanol. Yeah, that's good. Now, if we had a molecule like this, let's do a different molecule. Let's do something like this. All right, let's do that molecule. Longest chain is what? 5. So pentene. We're going to call it pentene. We don't have a way to handle the double bond as a substituent, so we're not going to do that. The ene is part of the parent name, so where does the double bond begin? On the second carbon. So we're going to number the chain based on the double bond, because that is the basis for this parent name. So what do we do with the hydroxyl? 4 hydroxyl. I kind of gave that away. 4 hydroxyl, 2 pentene. So there is a case there where we need to know what to call an OH as a substituent. Now we didn't need to do that here, because we can roll those right into the name, the parent name of the molecule. Doesn't have a double bond or anything else in it, so it's going to be an alcohol. And all right, so that's how you would handle those things. 4 hydroxyl, 2 pentene. Okay, primary, secondary, or tertiary? Primary, secondary, secondary, primary. Good, primary. You're seeing this over here, but that doesn't have anything to do with that OH. That OH is on that carbon, and we're not saying how many carbons are behind all of that, just how many carbons are directly attached to that carbon. There's only one. The consequence of that is that carbon has two hydrogens on it. And that's a primary. I heard a whole bunch of things. Tertiary. Tertiary. That has 1, 2, 3 carbons attached to it. So this is tertiary. This is primary. Secondary. Secondary. Primary. Okay, so maybe we will go in this order. I don't know. I'll have to see how we go here. You're familiar with this already. This is the hydration of an alkene. From alkenes, by adding water, we're talking hydration. Hydration of an alkene. Carbon-carbon double bond. You can produce an alcohol. You should be pretty familiar with this. We got it in chapter 11 as a reaction of alkenes. One of the 4 addition reactions of alkenes is the addition of water. And Markovnikov's rule predicts the major product in this situation. The hydrogen on the water goes to the carbon with the most hydrogens, and the OH of the water, the other part of the water molecule, the OH, goes on the other carbon. So here's propene. You get isopropyl alcohol as a major product and 1 propanol as the minor product. So probably around 90% or so is this, and 10% is that, which is probably why rubbing alcohol is inexpensive. You know, that's the primary product of the hydration of propene. So that's your first reaction, and you're already familiar with it. Okay, now we got to talk a little bit about this one because you haven't been introduced yet to this bond. This is chapter 13. We're going to talk about this. And if we have this sort of situation, this is a carbonyl. It's not a carbonol. A carbonol is an OH. A carbonyl is a carbon-oxygen double bond. Like I said, this is the whole subject of chapter 13. If that double bond, if that carbon-oxygen double bond is at the end of the molecule, it's an aldehyde. If that carbon-oxygen double bond is in the middle somewhere, not on the end, just say not on the end. The molecule could be 8 carbons long. Anywhere on the 2nd, 3rd, 4th carbon, if you had a carbon-oxygen double bond, you're talking about a ketone. All right? But whether it is an aldehyde or a ketone, there's something pretty common going on here. Okay, you already know this. The hydrogenation of a carbon double bond, right? What happens when that happens? Well, the hydrogen goes on one carbon, the hydrogen goes on the other carbon, and you eliminate these bonds, and you get an alkane. Well, let's just look at how similar it's going to be here. Okay, don't overcomplicate things. Build on what you already know. This is a carbon-oxygen double bond. And what's going to happen is a hydrogen is going to go on the oxygen, the other hydrogen is going to go on the carbon, and we're going to eliminate those bonds right there. All right? And what have we produced? We've produced an alcohol. By the hydrogenation of a carbon-oxygen double bond, you produce an alcohol. Not an alkane, because this right here is not a carbon. It's an oxygen. And an OH is a hydroxyl group. That converts it into an alcohol. So this is a way of making alcohols. The hydrogenation, that's the second one I got over there. The hydrogenation of a carbon-oxygen double bond. All right, so don't worry about naming aldehydes or ketones. You can worry about that next week when we get to chapter 13. Just kind of right now grasp the mechanism. What's going on here? Hydrogenation is the addition of hydrogen to a molecule. You can hydrogenate a carbon-oxygen double bond. You can hydrogenate a carbon-carbon double bond. You can hydrogenate a carbon-oxygen double bond. It's hydrogenation. You can use some of the same catalysts. Look at same catalysts. Do this that hydrogenate alkenes. So this is an aldehyde, and here's what you need to also carry along as you learn this. The carbon-oxygen double bond is on the end of the molecule. We're going to add a hydrogen right there. So what does that mean? We're going to put a hydrogen there and another hydrogen here. So where does that OH end up? On the end of the molecule, where the oxygen was to begin with. Yes? This means yes. All right? So if it is on the end, it's a primary alcohol. You hydrogenate an aldehyde, you get a primary alcohol. Now here is a molecule you'll get real familiar with in chapter 13, acetone. You'll get familiar with that one too. It's acetaldehyde. This is acetone. It's a ketone. You can see it here, kind of hear it in the name. Acetone, ketone. It's a ketone. It's got the carbon-oxygen double bond right in the middle. This is only 3 carbons long, and it's not on either end. It's in the middle. And we're going to put a hydrogen right there and another hydrogen right here. And that means the OH is going to end up in the middle. And so you hydrogenate a ketone plus hydrogen yields a secondary alcohol. An aldehyde plus hydrogen yields a primary alcohol. For your sake, if I gave you a reaction, maybe even gave you the molecules, I wrote out the molecule plus hydrogen yields what? Just keep this in mind. The OH should end up on the carbon that the oxygen was on to begin with. Nothing happens to that one bond right there. We add a hydrogen here and take away one bond, but that doesn't move. Stays right where it was to begin with. Okay? Likewise with the ketone. We're going to add a hydrogen right here. We're going to get rid of that bond right there, but that oxygen isn't going anywhere. It was on the second carbon to begin with. It's on the second carbon in the product. So just keep that in mind. So that's there. Now you know 2 ways of preparing alcohols. The hydration of a double bond, carbon-carbon double bond. The hydrogenation of a carbon-oxygen double bond. Yeah, like I said, don't worry about the names of these. Just do be aware right now that what is an aldehyde? An aldehyde is a carbon-oxygen double bond that is on the end. There's always going to be a hydrogen there. For an aldehyde, there'll be a hydrogen there all the time. For a ketone, there's no hydrogen. It has a carbon-oxygen double bond and then two carbons. In one way, shape, or form, there's no other hydrogen. Okay, go ahead and finish this. And name the alcohol. I won't say name the ketone, but name the alcohol that's produced. All right, so it's 6 carbons long. What are we going to have here on that carbon? An OH. And down here, an H. All right, so you've seen how a ketone is going to result in an alcohol. And what is the name of that? Hexanol. And it is a secondary alcohol. Well, start over on the right. Okay, start at the end, closest to it. 1, 2, 3. 1, 2, 3. Yep. So don't just start on the left. Start on whatever end is closest to the OH. Oh, here we go. All right, oxidation. Let's move on down. Let's move on down here to oxidation. I think they come in this order on your homework papers, but let's look at oxidation. In 1305, you learned that oxidation is the loss of electrons. Reduction is the gaining of electrons. We're going to, that's true. That's definitely true. In the organic environment, we're going to look at another way of looking at what is oxidation and reduction. We're going to use oxidizing agents like this. This is potassium dichromate. This is potassium permanganate. And in some cases, what you're going to see an arrow like this. And that general symbol sitting above the arrow, which is saying we're oxidizing something. Now, the way some of these problems can come at you is you've got this and you've got the product, and you have to write out what the reactant would be. Or you have the reactant and this, and you have to write out the product. Or you'll have a word sentence that says, write out the oxidation of, write out the chemical reaction for the oxidation of 1-hexanol, for example. So you got to put down 1-hexanol, draw an arrow, put the oxidizing agent, and then what would be the product. Okay, the three classes, here's the important thing here. The three classes of alcohols behave differently towards oxidizing agents. So we have to think about each one of them. All right, here is the, instead of the oxidation is the loss of electrons, reduction is the gaining of electrons. You're going to see this slide in chapter 12 right now, chapter 13, chapter 14. As we talk about things, notice this arrow moving in this direction is oxidation. This arrow coming back in the reverse direction is reduction. Okay, what is oxidation? It's the gaining of oxygen or the loss of hydrogen. And when we say usually two hydrogens. You gain an oxygen or lose 2 hydrogens, that's oxidation. Remember, that's or. Either one of those things happen, and you're talking about oxidation. Reduction is the exact opposite. The loss of oxygen or the gaining of 2 hydrogens is reduction. So what do we have here? We have an alkane going to an alcohol going to an aldehyde or a ketone going to a carboxylic acid. So we're getting a little bit ahead of ourselves. This is chapter 13. This is chapter 14. But here we are in chapter 12. I mean, this is chapter 12 because we're now going to talk about, you can take an alcohol and you can oxidize it to form an aldehyde or a ketone. Notice we got 1 oxygen on this alcohol. We only have 1 oxygen on this aldehyde or ketone. This happens to be an aldehyde. But we only got 1 oxygen. But what did we do? We lost 2 hydrogens. See that? Loss of 2 hydrogens. So that's oxidation. Going from an alcohol to an aldehyde is oxidation. The organic molecule is in a more oxidized form or state than it was as an alcohol. And obviously going from an alkane to an alcohol, we didn't look at a reaction on how to do that, but if you go from an alkane to an alcohol, what have you done? You've added oxygen, gained oxygen. So an alcohol is more oxidized than an alkane is. And then to go from an aldehyde back to an alcohol, which you already know in a reaction that does that, right here, hydrogenation. So you hydrogenate this, it adds hydrogen, puts a hydrogen there and a hydrogen there. That's reduction. So whenever you hydrogenate something, it's undergoing reduction because it's gaining hydrogen. I mean, by definition, when you hydrogenate something, it gains 2 hydrogens, it's being reduced. Okay, so this is the first time you're seeing this, but start kind of wrapping your mind around that. So you can say, oh yeah, okay, yeah. We're going from an alcohol to an aldehyde, that's oxidation. All right, so let's take this alcohol. This is 1-propanol. we've got a primary alcohol. And you could take a mild oxidizing agent, maybe at low temperatures, and you could carry this over to produce an aldehyde. And you can see we would have lost two hydrogens, one hydrogen. Oh yeah, this carbon is this carbon. So we would have lost two hydrogens, one and one of those, and gotten a carbon-oxygen double bond there, and that's oxidation. This could go further if it was, or you could use a stronger oxidizing agent, and it would kind of go to here. This thing here would carry it right through there to there. This is even more oxidized. That's a carboxylic acid. So a primary alcohol can undergo two steps of oxidation. Let me just show you that previous slide. So a primary alcohol can go to an aldehyde and then all the way over to a carboxylic acid. Oxidation, oxidation, further oxidation. Both of those are more oxidized forms of the original molecule. All right, so this is what we got on the next slide. This and this. This and this. All from a primary alcohol. So a primary alcohol can oxidize to an aldehyde, and it can further oxidize to a carboxylic acid. Or this is, let's move that up a little bit. So can go to this, and it can go to this. All right? We've lost two hydrogens. We've added another oxygen. Or added another oxygen. So addition of oxygen, loss of hydrogen, that's all oxidation. And we're starting here with a primary alcohol. So let's just take a real simple alcohol. Okay, complete the oxidation of ethanol. Why don't you take it through both steps? Oxidize it to an aldehyde and then oxidize it to the carboxylic acid. Again, ethanol is a primary alcohol. Okay, the very first step would just be something like that. Like I said, don't worry about naming these right now. We'll get into nomenclature of aldehydes and ketones in chapter 13. And then it will go, still just two carbons. If I give you this and say complete the oxidation of this, I think if you gave me either that or that, as the answer. For right now, it would be acceptable. It's not easy to stop here. This kind of slides right over there. So you have to kind of keep this at low temperatures. You have to use mild oxidizing agents. You have to be careful if this is where you want the reaction to stop. If you don't want the reaction to proceed all the way to the carboxylic acid, you have to do it carefully. But you can. It can be done. Okay, so there's the oxidation of a primary alcohol. Secondary alcohol. Here's your isopropyl alcohol. Secondary. Oxidizing agent. There is a hydrogen here. I mean, if we drew this molecule, this is what it would look like. Oh, I don't need double bond there. Single bond. That's what the molecule looks like to begin with. Isopropyl alcohol. 1, 2, 3, 4 bonds around it. And so what do you get? You get you eliminate, you lose these two hydrogens. And you form a carbon-oxygen double bond. Right where the OH was is now a carbon-oxygen double bond, no hydrogen. Right? 1, 2, 3, 4 bonds. So be careful in putting hydrogens all around your molecules. Count the bonds around the carbons. Don't ever have more than 4 bonds. And you should always have 4 bonds around every carbon. So a secondary alcohol oxidizes to a ketone, and that is it. Doesn't go any further. You know, you try to, you know, if you'd say, well, what about this? No reaction. You can't oxidize the ketone any further. It doesn't go through 2 steps, just 1 step. Ketone, and the reaction is done. Okay, we'll summarize all 3 of these, primary, secondary, and tertiary, in just a second. Well, let's do one. Well, let's do a tough one. Here's a secondary alcohol. What is that going to produce? Let me see some of your drawings. Those 2 hydrogens. Yeah, there you go. Okay, put your hydrogens on there. This is a secondary alcohol, right? This is cyclohexanol. It's a secondary alcohol. So you'll get the carbon. Well, you're going to get, remember, you're going to get the double bond right there. Carbon-oxygen double bond is going to be right there. Yes. Good. Yeah, there you go. Okay? Count the bonds around that carbon. Well, how many are there? 1, 2, 3, 4, 5. There you go. Okay? See, it has to lose 2 hydrogens.
Oh, okay.
It's going to lose those 2 hydrogens and form that double bond. Yes. No, it's not going to go there. But what are we producing in these things? We're producing that bond, carbon-oxygen bond. And we're not forming an alkene. We're forming a ketone, which is a carbon-oxygen double bond. Yeah, right where the oxygen was to begin with. Yeah, okay, you see? All right. So right where that oxygen was to begin with, I should write these in here like this. Oh, I love this. Carbon. That's good. All right, right where that oxygen was to begin with, we're going to get a carbon-oxygen double bond. And a lot of times students will ask, well, where'd the hydrogens go? And I'm not even sure I know the answer to that. It gets sopped up in this oxidizing agent. The hydrogens, it doesn't really come off as hydrogen gas necessarily. It gets caught up with the oxidizing agent. So don't worry about balancing that. I mean, typically I have you figure out what got lost and included somehow, but don't worry about it too much in this case. But you can see there's no hydrogen on that carbon. It lost those 2 hydrogens. This is that's cyclohexanone. It's a ketone, cyclohexanone. I said don't worry about naming them, so don't worry about that. You can ignore that I said that. But that's what you get, okay? And you don't need to know the name. You just need to know, how does this proceed? This is how it proceeds. Where you got an OH, you end up with a carbon-oxygen double bond. And you're losing 2 hydrogens. Okay. Tertiary alcohol. You're going to love this. Tertiary alcohol. This is T-butyl alcohol right here. No reaction. Does not oxidize. Tertiary alcohols do not oxidize. There's no hydrogen on this carbon right here. So that's kind of what you need for the oxidation to proceed. You need to lose 2 hydrogens. There's no hydrogen. There's a carbon, and a carbon, and a hydroxyl. So tertiary alcohols don't oxidize. So here's the neat little summary. Primary alcohol oxidizes to an aldehyde and then to a carboxylic acid. Let's see, I'll write it like that. Secondary alcohol oxidizes to a ketone and that's it. Stops right there. Tertiary alcohol does not oxidize. No reaction. I'll tell you what. Let's take not take a break, but we can take a break. But let's just you take out your chapter 12 homework and do question number 5. Finish question number 5 and take a break between now and about 5 to 3. All right? We haven't gone over question 4 yet. That's going to be our last thing. No, I don't know that. All right. The last reaction here, I think the last one, is the dehydration of an alcohol. And we're going to learn a new rule here, Zaitsev's rule. And there's going to be some situations, where there is a major and minor product. So this is an elimination reaction. We're eliminating an entire water molecule. So let me take a simple alcohol where you're actually can only get one product. An alcohol in the presence of a strong acid will dehydrate to form an alkene. This kind of reaction in which 2 or more covalent bonds are broken and a new bond is formed is called an elimination reaction. And what is being eliminated is a water molecule. A water molecule is eliminated from an alcohol. When more than one product is possible, then you use this Zaitsev's rule. But let's not worry about that rule right now. Let's look at a situation when you only can get one product. So let's take one of our favorite alcohols. Not one of our favorite alcohols, but one of the most common ones. And I'm going to put a hydrogen here, and I'm going to put a hydrogen here. And these are also hydrogens, which I'm not going to necessarily write out there. But we're going to eliminate a water molecule. And the way we're going to eliminate it is between 2 adjacent carbons. One of the carbons holds the hydroxyl, and the other carbon has a hydrogen. So H2O. There's water right there. Right? There's a water molecule sitting right there, or right there. I probably should have drawn this right in the middle of the paper, because if I eliminate that, what's going to happen, one of these electrons is going to come down into here, one of these electrons is going to come down into here, and we're going to form our water molecule, and the other electron is going to go up into there. All right, so we're breaking 2 covalent bonds here, forming 2 new bonds. One's going to be a carbon-carbon double bond, and one's going to be a hydrogen-oxygen bond to form the water molecule. So this product would be this. Or I could split that water molecule out. That OH could decide to go with that hydrogen. And what would I get? Now, is that different from that? Yes? No? No. No. No, if you named that, it would be 1 propene. If you named that, it would be 1 propene. Those are the same molecule. So although in this particular situation, we don't really know which hydrogen it took, or actually, half the time it could take that one off to its right, half the time it could take the one off to its left, but we get the same product. We get a double bond on the end and a methyl, so a 3-carbon long alkene. So Zaitsev's rule is we don't even have to think about it here. There's only one possible product. Okay, so let's take another alcohol. Yeah, let's take another alcohol. Let's just add one more carbon to this thing. I'll write it in the middle this time. And we'll put the OH right here. And I'm going to write the hydrogens that are on either side of it. And let's see what the situation is here. All right? Same sort of thing. It's always going to be that it's the OH on one carbon and a hydrogen on an adjacent carbon. That's what's eliminating out of this molecule, a water molecule. It doesn't just take a hydrogen anywhere. It has to be next to this carbon. All right, so we could take that one out right there. And the double bond is going to go right here, right? So let's draw that one here. Or I'll put a square around it this time. We could take that hydrogen. This OH could decide to eliminate with that hydrogen. In which case, so this one gets us here. This one gets us somewhere else. We get the double bond. The double bond's going to form between the two carbons where the water eliminated. Right there. Those are different, aren't they? Those are different molecules. This is 1 butene, and this one is 2 butene. And those are two distinctly different products. And let's see, one is major and one is minor. So let's see what this Zaitsev's rule says. The product, Zaitsev's rule, the product that gives the highest number of carbons attached to the double bond is the major product. The product that gives the highest number of carbons attached to the double bond is the major product. So here's our double bond here. This double bond has a hydrogen. All right, and we're not going to count that carbon. We're saying how many carbons are attached to this double bond? 1. Don't count and say, oh, there's 2 of them attached. No, directly attached to it, 1. Here's your double bond here. How many carbons are attached to this double bond? This carbon has a carbon. That's 1. This carbon has a carbon. That's another 1. 1 and another 1 is 2. So which molecule has the most carbons on the double bond? The 2-butene. This has the most carbons attached to the double bond. This is the major product. It's a major product. And this would be the minor product. So when you dehydrate 2-butanol, the major product is 2-butene. Okay, now you'll see Zaitsev's rule said in a couple ways. Either here, the highest number of carbons attached to the double bond. So what you're looking at is a double bond, and a double bond is going to have 4 things around it. It can be hydrogens or carbons. You're looking for what are these 4? And you're looking for the most carbons that are attached. Sometimes they'll say this in another way, the most substituted. double bond is the major product. Most substituted. Well, substituted, we're not talking about hydrogens, we're talking about substituents or carbons attached to it. It's just another way of saying it. All right, so here's another alcohol here. The 1, 2, 3, 4. This is 2-butanol. It's 2-butanol. It's 3-methyl-2-butanol. It's got a methyl group here. Here's your acid. Sulfuric acid is a dehydrating. It really sucks up the water. It's a dehydrating acid. There's a hydrogen on this. There's 3 hydrogens. So you got 1, 2, 3. You got a hydrogen sitting right here. You've got this hydrogen sitting right here. So you can get a water molecule out of here, or you could get a water molecule here. You get the double bond here or the double bond here. So, double bond here is this product. The OH was there, and this hydrogen went with it. You got a double bond. Here's where the OH was here, and it left with one of the hydrogens over here. You got a double bond on the end now. All right, so this only has 1 carbon directly attached to it. And don't worry about how big this group is. It's only got 1, it's substituted with 1 carbon and 1, 2, 3 hydrogens around it. So that's what that double bond looks like. It's got a hydrogen, a hydrogen, a hydrogen, and then it has just 1 carbon. And then the rest of this stuff. So it only has 1 carbon on it. But this one up here has 3 carbons on it. This is the more highly substituted double bond. It's the more stable double bond, and it's the major product. Okay, so that's Zaitse's rule. This is the dehydration of alcohols to form alkenes. Okay, this one, yeah. You've got a hydrogen here, so you could get your water molecule here and form a double bond right there, or you could that has a hydrogen on it, so you could get your water molecule right there and form your double bond right there. And you see how they're saying that is going to be the major product. Why? Because now this double bond has a carbon, and another carbon. It has 3 carbons substituted on that double bond. That's the major product. If we had formed the double bond right here, it would have had 1, 2 carbons on it. But this one would have 3, so it is the major, this is the major product. Oh yeah, we do have another reaction. Okay, we got another reaction. I don't have it on the homework. Go ahead now. Go ahead now and do problem number 4. You got 3 molecules there. They're all alcohols. I'm sorry, I don't have a lot of room, so don't feel like you have to write out the whole reaction. If you want to kind of make a small little drawing of that alcohol and then draw next to it the major, it's going to be an alkene. So draw next to it the major product from the dehydration of that alcohol that's listed right there. So don't make a big, long reaction. Just your alcohol, your major product. Alcohol, major product. If you need to scratch it out on a piece of scratch paper to figure out what is going to be the major product, go ahead and do that. Then transfer it onto this paper. Yes, I am. There is another part here, ethers. How many more slides are there? Oh, another 20 slides? You got to be kidding me. All right, you're killing me, Larry. 20 more slides. Okay, ethers. This chapter 12 is about alcohols and ethers. So, ethers. This is also a dehydration reaction. What is an ether? An ether is this. That's the general formula of an ether. It's a carbon-oxygen-carbon bond. It's an oxygen stuck between two carbons. And this is an ether. So if you've ever gone to the dentist and they said, "Oh, we're going to put you under ether," it's this kind of a compound. This is a class of organic compounds. There's all kinds of ethers. The simplest one would be this one right here. And it would be dimethyl ether. So we know we got an oxygen between two carbons. We're asking ourselves the question, what's on either side of the oxygen? Well, there's a methyl group on each side of the oxygen. So it's dimethyl ether. This would be a simple ether and a simple name of an ether. And if you can get away with a simple name, get away with it. Like either it could be methyl ethyl ether, diethyl ether, methyl isopropyl ether. Those would, if you can take a simple substituent and see it on either side of the oxygen, then you can give it a simple name. We'll get into IUPAC names here in a minute. Two alcohols can also react in the presence of an acid to form an ether. There are ether linkages in many important in carbohydrate, fats, proteins, many other essential substances. There can be these ether linkages. So you can dehydrate an alcohol and either form an alkene, which what we just did, and you wrote them out on question number 4. That is dehydrating, that's taking a water molecule out of one molecule, and you form an alkene. This, to form an ether, you're dehydrating between two alcohols. For example, if I wanted to make dimethyl ether, I would take methanol and I would eliminate a water molecule from between two alcohol molecules. And what would I get? You can see that oxygen stays, this bond breaks, and that goes there, and we get a water molecule. There's our water molecule, and there's our ether. So it is dehydration. We are eliminating a water molecule, but the half of the water molecule is coming from one alcohol molecule, and the other part of it is coming from another one. So there are two alcohol molecules involved in this to form an ether. To form an alkene, it's just one molecule. You're getting the water molecule out of one molecule. All right, so that would be, so methanol plus methanol forms dimethyl ether plus water. All right, so okay, methanol, you can't form an alkene out of methanol. All right, you need two carbons. So the only thing you could do is form an ether by dehydrating between methanol. But if you had an alcohol where you could form an alkene, you by the reaction conditions, you could direct it to either produce ethers at lower temperatures or alkenes at higher temperatures. Oh, we probably should. There got to be some more examples. I thought there were going to be some more examples here of ethers. 37? Okay. Yeah, we'll come back and look at our summary. Oh, they must have gotten mixed up. Oh, there we go. There's ethers. Okay. I'll get back to those others. Ethers have a general formula, ROR. So there's dimethyl ether right there. They're slightly polar. They're not as polar as alcohols. Because why? That oxygen doesn't have a hydrogen on it. There's no hydrogen on this oxygen. So the OH bond is highly polar. The CO bond is not as polar as an OH bond. And so there's no hydrogen here. So these are a little bit polar, but not as, more polar than alkanes, not as polar as alcohols. And again, when I talk about polarity, your eyes are going to roll later because you're going to always say, oh, he's going to talk about boiling points again. Yep, yeah. All right, so here's butane, about 0 degrees centigrade. Here is, so 4 carbons. So I've got 3 carbons here in an oxygen. Why did I go to 3? Well, that's about the molecular weight of butane. So similar molecular weight molecules, if all other things are equal, should have comparable boiling points. Well, obviously, other things aren't equal. This boils at about 0. This boils at almost 100. 100 degrees higher. Because of that H on that oxygen being polar makes that molecule have an attraction for the other molecules that are around it, like itself, and it takes energy to break that attraction and get it to boil. Well, here's 3 carbons and an oxygen, exactly the same molecular weight as 1-propanol, but notice it only upped the boiling point 8 degrees. 8 degrees higher boiling point, 100 degrees higher there. Why? Because there's no hydrogen on that oxygen. Little bit of polarity, but not a lot. Common names of ethers. Name these. Do I have the names on these? Yeah, there we go. Yeah, like I said, if you can see the simple substituent, that's a methyl, that's an isopropyl. So what we're going to call it, isopropyl methyl ether. Remember, just in chapter 11, we learned that a benzene ring as a substituent is called a phenyl. So here's an ethyl phenyl ether. Ethyl phenyl ether. I wouldn't necessarily say you got to have 3x5 cards for those. I don't know. Just kind of be aware. When you can name an ether simply, use a simple name. Now, we'll talk IUPAC, and you'll see it can get a little bit more complicated, like right here. Here we go. We got a methyl over there. You say, well, that's pretty simple. But now we've got 1, 2, 3, 4, 5 carbons over here. We're not going to call it just pentyl methyl ether because I wouldn't know whether this is attached here or right there on the end. It just leaves too much ambiguity. So here's an IUPAC name. And what are they doing? They're taking this thing, and they're not calling it a methyl group. They're calling it a methoxy, methoxy group. So this right here is a methoxy group. This is an ethoxy group, ethoxy. And I wouldn't worry about anything more than that. So we've got pentane, 1, 2, 3, 4, 5, pentane. And we've got a methoxy group on the first carbon. So it's 1-methoxypentane.
You wouldn't put the ethyl at the end?
Wouldn't put the what?
Ethyl at the end?
No, you wouldn't add ether to this name. Just when you got like dimethyl ether, isopropyl methyl ether, we can see that this is an ether. There's a carbon-oxygen-carbon bond. I just want to quickly, let's put 5 carbons here, and let's put this group right here. Just to show you how this IUPAC naming is a little bit more versatile. Now what we have here is 2-methoxy pentane. All right, it's still pentane, but the methoxy is hanging off of the second carbon, not the first. So these are ethers. Reactivity ethers, don't worry too much about this. You can burn them. As a matter of fact, they're very combustible. You got to be careful with ethers. Low molecular weight ethers give off a lot of vapors, and they're very combustible. You know, spark, static spark or whatever. So you can burn them. This is showing you how to make an ether. An alcohol plus an alcohol forms an ether plus water. So if we had ethanol and an acid, we could form diethyl ether. We're not going to do a deep dive into ethers. I mean, don't feel like this is a major portion of this chapter. Just be aware of what ethers are. They form by the reaction of two alcohol molecules with each other. And okay, anesthetics. Penthrane is an anesthetic. It's a methyl, and here we have difluorochloroethyl ether. Penthrane. Diethyl ether, first successful general anesthetic. So whether in an operating room or dentists, this is a common solvent in an organic laboratory, diethyl ether. So you have to be, you got to use it in the hood, got to be careful. You're going to get a little woozy. It can, it's an anesthetic. I think I mentioned to you about the master's level nurse anesthetist. Did I mention that person to you? I was flying on a plane, military guy. We're sitting next to each other. I said, "Oh, what do you do?" I said, I'm a nurse anesthetist. I'm actually going off to a conference for nurse anesthetists. Oh, wow. I said, what are some of the anesthetics? And he started writing a whole bunch of different things down. And why do you use one versus another? He said, well, we have to know the solubility of this in the bloodstream. We have to know the vapor pressure of this. How long is it going to take to exhale it once we put a patient under? Is it going to go into the bloodstream, make them go unconscious for 5 minutes, 20 minutes, 3 hours, 7 hours? How long is it going to take the body to eliminate that? So what this is doing is it isn't necessarily reacting in the body. It is going to some receptors and anesthetizing, but it's then being released off of those receptors and carried to the lungs where you generally are exhaling it. And he said the doctor tells us, okay, I don't want this patient to be awake for 4 hours. So we have to figure out which anesthetic to give. So there's a whole family of anesthetics, different molecular weights, different vapor pressures. Okay, thiols. I said there's 20 slides. So sometimes I forget what's all in a particular chapter, and now I'm remembering. Okay, this is a thiol, where an OH is an alcohol, an OH group, an SH group is a thiol. That's about all you need to, that's the main thing you need to learn. You might have a question. Which of the following functional groups is a thiol? I can have an OH, an NH2, a bunch of stuff there, and an SH. You go, oh, the SH, that's the thiol right there. These sulfur is right below oxygen, so this forms an OH group to make an alcohol. An SH group forms a thiol. This is important in proteins. Cysteine is a thiol functional amino acid, cysteine. These, where alcohols have certain properties, thiols usually have really an offensive odor, very offensive. The North American skunk produces thiols, and we are activated. Our olfactory glands are activated in the parts per billion of these thiols that skunks produce. So you don't need to smell a lot of it, and you smell it. It will diminish if you stay in a thiol, a very offensive thiol atmosphere for 30, 40 minutes, an hour. You go, I don't smell it anymore. Pepe Le Pew doesn't smell himself, okay? He said, what's everybody bothered by, He doesn't get it. Pepe Le Pew. So there's your thiol. your thiol. These are molecules that he produces, he manufactures. And the alcohols, similar alcohols, are the fragrance coming off of roses. So there you go. Substitute that sulfur with an oxygen. Don't worry too much about it. Ethane, thiol. What do we got here? 3-methyl, 1-butane, thiol. But I'm not going to give you too many things like that. I just want you to know what a thiol is. Here's the thing. We'll get to this in chapter 18. Cysteine, this is an amino acid. It's got a thiol functional group on it. And in protein synthesis, this is a very critical bond that's forming, a disulfide bridge. But like I said, in chapter 18, we'll do a deep dive on that. Just want you to know. So here's representing a protein molecule. Here you would have a cysteine here, and it's forming this disulfide bridge to create as a matter of fact, insulin. Insulin has a number of these at very key locations in the insulin protein molecule. Okay, we need to go back to a few more slides here. What did I skip over? I skipped over this. An aromatic alcohol. Now you should have a 3x5 card on this. So you should have a phenol, and then your structure of phenol. It's an aromatic ring, benzene ring, with an OH on it. That's an aromatic alcohol, phenol. All right, not to be confused with phenol, which is a benzene ring substituent on a molecule. This is actually a compound, phenol. So there you go, phenol. It shows up in different places. Hexachlorophene this is kind of a phenol with chlorines on it, bounded to another one. There's hexachlorophene. It's an antiseptic. This is the only one you have to memorize the name and structure of. All antiseptics. Hexoresorcinol, orthophenol, phenol. All right, you don't need to worry too much about special reactions of phenols. All right, I think I will close this down. Oh, we had some reaction summaries here at the end, chapter 12. Where are they? Yeah, these are kind of neat little things. So an alcohol. How do you prepare an alcohol? Well, you can do the hydration of an alkene and produce an alcohol. You can do the reduction of, remember the carbonyl is this bond. So that's an aldehyde or a ketone. That's hydrogenation. Hydrogenation is reduction. You're adding hydrogen. That'll form an alcohol. Then what else do alcohols do? They oxidize. I guess this doesn't have everything on it. A primary alcohol will oxidize to an aldehyde, which then will go to a carboxylic acid. Primary. So I don't know why they don't just use this. Secondary alcohol is going to oxidize to a ketone. A tertiary alcohol is not going to oxidize. Dehydration of an alcohol, and you get an alkene, and you need to use Zaitsev's rule. I think I'm misspelling his name. Zaitsev. Zaitsev. Is that another Z or an S? Zaitsev. Oh well. A Z? Two Z's? Zaitsev. S. It's an S. Oh, we can change that. Zaitsev's rule. Okay, so I'm not sure that captured everything, but most of it. There's a listing in words, and then at the end of your book, I'm not sure what edition this is, but your book should have this sort of thing too. There is the hydration of an alkene to form an alcohol, the hydrogenation of a carbonyl to form, so this can be an aldehyde or a ketone. You're going to get a primary or secondary alcohol. A dehydration of an alcohol to form an alkene in water. Now here's the dehydration synthesis of an ether. Alcohol plus an alcohol forms an ether plus water. And then there's your three oxidations. Primary to an aldehyde, secondary to a ketone, tertiary, no reaction. So that's a pretty good reaction summary.